Yeah, thanks. So I'm an oceanographer. I'm going to talk to you about plastics in the ocean, but I'm more interested in anything about the ocean. So I'm interested in currents and how ocean moves stuff around. And of course that is also very relevant to climate. We're here in a climate institute. We're here in the Grantham Institute of Climate Change and the Environment. And I just want to highlight that, yes, I am also a climate scientist. I'm actually a climate scientist that was on YouTube. Anyway, thank you. That was quite fun to do. I had a towel under the desk, and between every shot I had to tussle my hair again so that it would keep standing up enough. It was really cool. Anyway, but that's, as I said, not what we're going to talk about. We're going to talk about this stuff. Plastics in the ocean. These are just two photos that are kind of like stock images. You've seen them all. There's whole lots of plastics in the ocean. But this is going to be a slightly more complicated talk than you would think. I'm not just going to say plastic in the ocean is bad. I'm actually going to touch upon some of the myths, and I hope to dispel some of the myths that are really out there. The most important of all is this idea of islands of trash. This idea that there's huge new content. There's NGOs out there that are called the seventh continent, with the idea that they are going to plant a flag somewhere in the middle of the ocean on a lot of floating trash. This is floating trash. But as you can see, there's always people there. That is because floating trash, the amount in the concentrations that you see here, is near coastlines. And I think that if there's one thing you want to get away, hopefully, from this half hour, is that plastic does harm near our coastlines. Plastic does harm right after it's being released into the ocean, after it gets into the ocean. That also means that it is our own plastic that does most harm. It's not somebody else's plastic. Especially when I still worked in Australia, there was a lot of talk about all these dirty Asian countries that would have an impact on Australian beaches. And we've now working on a paper. I'm not going to show it here because it's really, really early work in progress. But essentially we're saying all the plastic you find on an Australian beach is Australian plastic. It's your own problem. Anyway, so just to bring that point home, there's a lot of plastic in the Thames. And plastic in the Thames is a really big problem, of course. So here you see all this dirty plastic. So what is plastic, right? I am not against plastic. I think plastic is one of the best materials ever invented. You couldn't. It's a bit of a platitude to say it, but you can't think of a society. You can't think of our modern society without plastic. Plastic is everywhere, and that's the reason. It's just because it's an absolutely fantastic material. It's lightweight. It's durable. It's waterproof. It's versatile, and it's cheap. But all of these things also make that it is really hard to get rid of in the environment. Plastic production has skyrocketed. So this comes is a graph from the plastic industry itself. And since 1950s or so until 2000, the amount of plastic has exponentially increased, and there's no stopping to it. Some people sometimes ask me, like, how does this relate then to oil production and everything? But to most plastic still is a byproduct of oil, essentially, right? So there's not really a connection yet between the amount of drillable fossil fuels and the amount of plastics we can produce. There's still plenty of raw material that we can work with. This will just go up and up and up. The problem with plastic is, of course, what happens after you've used it. The problem with plastic is that it doesn't have a value to us. The old plastic, except for, interestingly, Lego. And I was yesterday at a workshop organized by the Department of Humanities in Southampton about how can we actually make value, how can we make plastic valuable. And I think Lego is one of the very, very few plastic products that keeps its value. Probably all of you still have their Lego from when they were young, right? It's ridiculous if you think about it. Why would you even keep it? It is because it has not an economic, but an intrinsic value. Anyway, so yeah, my head is really spinning because I'm writing this really big grant. So I have all this information in it, and everything is just going to come out in this half hour. Sorry, it might not every time seem sense, but there is kind of a line through it. So anyway, so the problem with plastic is, what do you do after you've used it? And if you would be nice, and if you would be clean, and if society wouldn't be as atrocious as it is, that wouldn't be a problem itself too, because we know what you can do with plastic. Nowadays, incineration is actually really good use of plastic at the end of its life. You even get some energy back from it, and the carcinogens or so is kind of solved. So we know that just putting plastics in a big burner and burning it out and getting some energy from that would be a nice way. The problem is, it just ends up in our environment. And the problem is some of it ends up in our environment. And I'll say later that actually it's a very large amount of it that will end up in its environment. If it gets into the ocean, it ends up there. And now this cuts into the story about the garbage patches. About these islands of trash. Probably most of you have heard about them. These areas in the middle of the ocean where all the plastic accumulates, and over time you get more and more and more. Now this is what an island of trash looks like. This is an expedition led by Charles Moore, who's literally a pirate captain. Well, I mean, he literally looks like a pirate captain. And he went out with his ship, a sail ship, into the middle of the garbage patch, the middle halfway between Hawaii and California. I'll show you later where it is. And he was looking for the amount of plastics that you see there. He had a trawl, a zooplankton trawl, so that's kind of like there's an opening this size or so, long net behind it, and he trawled it through the ocean for 1 mile, 1 nautical mile, so almost 2 kilometers. And then at the end, when he collected it all up, he sieved through everything that was at the end of his trawl net, and this is what he came up with. This is the amount of plastic you find in the most polluted hotspot in the open ocean. This is the garbage patches. It is a few tiny, tiny pieces. It is small kind of stuff. It is nothing compared to these photos that you see closer to shore, that you see in the Indonesian seas, that you see here in the Thames, that you see in the North Sea even. It is very tiny, it is very small. So let's take a step back and try and think about what happens to plastic. What is plastic in our ocean? What's really the problem of it? And really it starts with 3 sources of plastic in the ocean. There's the famous one, the plastic waste, everybody knows about. Bottles, rubber duckies even if you want it, everything is there. Things that are big and that we throw, that we don't properly discard with. Then there's a second one, which used to be a really problem, but it's actually one of the biggest success stories now, microbeads. Microbeads are tiny plastic pellets that are in scrubs and that are used to kind of like provide a scrub feature of fancy cosmetics. Now there was a really big outcry of it, and many jurisdictions, including the EU, have now just simply outlawed them. It is illegal to sell scrubs with plastics in it. Now they're using sand or coconut material or something like that. So that was all because of public pressure, of people saying, well, it's ridiculous that I'm buying a product whose design it is to wash down the drain at the end in micrometer size, which is actually, as I'll come to later, probably one of the biggest problems. Smaller plastic is probably more important than bigger plastic. And then finally, another really big source that's, of plastic that's getting more and more attention now is fibers. So these are even smaller than the microplastics, and they are really nanometer size. They come mainly from outdoor sportswear, Gore-Tex, those kind of like nylon, synthetic fibers that a lot of you here are using. Every time you wash them and you put them in especially a tumble dryer or something, it's the washing that's actually a problem. If it gets worse, tiny fibers break off and they wash with the sewage into the sewage treatment plant. Now we don't really know how much of that gets filtered out. That's actually one of the worst PhD projects I've ever heard about. Was some poor PhD student who needed to find out the efficiency of a sewage treatment plant of taking nanoplastic out of the sewage. So that means that both measuring after and before and trying to find out and trying to go through it, counting the amount of microfibers. Poor student. But anyway, so we don't really know how much of the plastic actually gets taken out by the sewage treatment plant. But we do know that there are still microfibers or nanofibers after sewage is flushed into rivers. And this is likely a very, very big source of plastics into our ocean. Now then, all of this, so this breaks down by the sun and the waves and then becomes small, and at some time, and we don't really know how long, but probably a few years, a lot of it is really small, right? And then it becomes microplastics or nanoplastics or whatever you want to call it. Then, about the impacts. So the big stuff here directly impacts big fish and big marine life because it can entangle turtles like here, or seals, or sharks. And there's no stopping on Google Images of poor sea animals with constrained or contracted with plastic, big plastic stuff. But the other thing is ingestion. And ingestion is probably a much more widespread problem because almost everything eats plastic, actually. We've seen now plankton, zooplankton, eating lots of plastic. Filter feeders particularly, things like oysters, have plastics in them. And it's really, really unclear what that does. We don't know what the impact is. And please, at the end, don't ask me about ecotoxicological impacts because it's a really complicated story. Last thing we want to do as a community of people studying plastic is to scare people away from eating fish. Fish is very healthy, fish is very important, and in loads of countries, fish is a crucial part of the diet. And you don't want to have people scared away by plastic. So that's a complicated story. But we do find plastic everywhere we look. Every time we open up an animal, there's plastic in its gut, essentially. So it is very widespread, and I'll come to that later a little bit. So my interest is about how plastic moves through the ocean. I'm interested in how, if you would start out with your plastic somewhere, how it moves, first of all, at the surface of the ocean, and then maybe after that sinks to the ocean, washes up on beaches, gets ingested. Problem, of course, is that we can't just follow tiny pieces of microplastic, but we can follow the water, hopefully, and we can. So the leap of faith I've made when I went into this research, which is actually only a few years ago, was that buoys, drifting buoys that we have on the ocean that drift with the flow, that they are representative of all the other small stuff floating around. Now the good thing is that these buoys, and they are here, they have a GPS on them and a satellite telephone. And if we throw them overboard like this, then they start they start transmitting their position. And if they then get into the ocean and they become something like this, with here the drifting buoy on the top, and then here a long sea anchor. And that sea anchor is there really to make the buoy more representative of the ocean flow, rather than just wind-driven, kind of like a ball in the wind. So it integrates out the Ekman spiral, is essentially the technical term for it. Now, one kind of cool experiment that we did 2 years ago that I led was when I was on an expedition from New Zealand to Antarctica. And as we went towards Antarctica on the in-way of the expedition, which in itself turned out to be a rather big crisis, but this part was still good, I had 20 of these drifting buoys. And these drifting buoys, I threw them in the ocean. I threw them in pairs, so there were 10 pairs. And every time I got them in the ocean, I had 2 volunteers standing on either side of the stern on the ship, I would say 1, 2, 3, go, and I would throw them in the ocean at exactly the same moment, 13 meters roughly apart. And every time that happened, they were 13 meters apart. And then they started transmitting. And they started moving around in the ocean. And it's just by itself, it just shows you how beautiful oceanography is, because there's all these scales of motion that come into play. So this is roughly 500 kilometers or so, to give you a bit of feeling. They start flowing with the ocean. And you see that where they started right on top of each other, which is 10 dots. Now there's suddenly 20 dots, because they started dispersing. They started moving away from each other. And over time, they started doing all this complicated kind of like circulation. And again, I want to draw your attention to this, which is by far my favorite. It's a threesome doing some kind of complicated tango around each other, really beautifully.
How many times have you looked at that?
Hundreds. It is just beautiful, right? It's the first time somebody did this in the Southern Ocean, and it just got published a few weeks ago or so. And so why is this then important? Why is this important to plastic? Well, it's important because it says something about the predictability of ocean flows. It says something about how sure you can be if you throw a rubber ducky or a plastic bottle somewhere in the ocean, where it is sometime later. So this chaotic nature of the ocean is seen in this movie, because it shows you that even if you start two drifting buoys 13 meters apart, by the time you're a month in, they're 400 kilometers apart. That is how fast the ocean disperses things. That is how chaotic the ocean is. This is, by the way, also my venture into media, essentially, because I made this plot a few days before Malaysian Airlines 370 got missing, and I showed it to a journalist who was not at all interested initially, but then came back because he said, well, you know something about how debris would float on the ocean, and you know something about how quickly things disperse and how easy it is to track, if you would ever find a piece of debris of MH370, how easy it is to find that back and to track that back. This shows you that it is actually really, really complicated. So it's not only those 20 buoys. There's actually a whole big program, and it's been going since the early 90s, essentially. This is just the entire array of buoys. It's maintained mainly by NOAA in Miami, but the UK Met Office is also a big contributor to this program, throwing in buoys everywhere, floating on the surface, moving around, really beautiful features. Now, if you look carefully, and if I may be able to convince you that actually these buoys, they accumulate. They kind of like hang around in this area for quite a while. They hang around in this area for quite a while. They hang around maybe even here, kind of like not moving anymore. Now, these areas are where we know that there's a lot of plastic. So the idea was maybe these buoys move to the same areas as where the plastic is. And then the next step in this story is that then we used the drifting buoys, 17,000 individual drifting buoy trajectories, and used that in a statistical, use them to say something about how plastic would move from any coastline to any other point in the ocean. Now, there's one big problem with these buoys, is that their battery is only finite. The battery time is really only 5-6 years maybe or so. After that, you can still, they still move around, but we don't know where they are anymore, so we can't track them. And that's a problem because the timescales over which plastic moves from one ocean to the other ocean is dozens of years, decades, maybe centuries. So you can't use any single buoy to tell you how water flows from one location in the ocean to the other location. But the thing that we used was we used some statistics. We used a transit matrix approach, essentially, and we're not going to go in it. I can go in it later if you want. But we used a transit matrix approach, statistics, to say something about how the statistics of these buoys move around. And that completely freed us from the individual buoy trajectories, and we could suddenly go much longer. That's what we did here. We did an experiment where we assumed that plastic gets in the ocean in one go. All the plastic ever into the ocean is just dumped as one kind of like pulse function, and after that there would be no more plastic. Well, when we wanted to do that, we had a problem that nobody knows where plastic actually gets into the ocean. So the assumption we made here was that more people near the coast means more plastic in the ocean. It was a really simple linear relationship between the amount of people near the coast and the amount of plastic in the ocean. So that's why you see really big amounts of plastic release here on the east coast of China, here, Java, here, Sao Paulo and Rio, everything, India of course. Now the transit matrix approach allowed us to just move this forward in time. And this is what plastic would then look like, according to the drifting buoys. And see that after, so we're now 5 years in or so, you start seeing accumulation. You start seeing that actually a lot of it starts to converge in this area. But it's not only this area, there's another area here, there's a tiny area here, there's an area here, there's an area here. There might even be a hint of an area here. And 2 weeks ago, so in this paper, we were the first to propose maybe there's a 6th garbage patch. Maybe there's a 6th accumulation zone in the Nordic seas. And actually, a few weeks ago, there was a paper came out that for the first time actually documented elevated amounts of plastic in this area too. So anyway, so there's 5 garbage patches in the subtropical ocean and maybe a 6th one here in the Barents Sea up north. So then the question is, of course, first, before we start analyzing this further, is are we doing any good? Actually, does this relate to anything we know about where plastic is in the ocean? Now, we know very, very little about how much plastic there is in the ocean, but we know quite a bit about the North Pacific garbage patch, because everybody loves going there, and all the NGOs love trawling through here and saying how horrible it is. So this is now a map of the amount of plastic in the North Pacific Ocean. The blue is almost no plastic, and it goes up to 500,000 pieces of plastic in a square kilometer. Remind you that there's 1 million square meters in a square kilometer, right? So this is the biggest densities we found are up to 1 million pieces per square kilometer. Anyway, the black line here is where we, 2 years before, said was the location of the garbage patch. Actually, it resembles pretty well what these observations later confirmed, that it is roughly the right extent. Unfortunately, or maybe fortunately, they didn't go much further westward, so we don't know how far we got out here, but at least the meridional extent we were pretty good at. We pretty well got that, I would say. So then if we believe it, so again, this is all observational drifting buoy data. We can go even further in time than 50 years, and we can go to hundreds of years of timescales. And we can actually start asking questions about how accumulating are the garbage patches? How much are they the kind of like the one-all and end-all of garbage? How much are they the black holes of garbage where nothing leaves anymore? And when we first showed this was actually a big surprise to the oceanographic community, because it showed that garbage patches are not at all stationary. So some grow very, like the South Pacific, which by 25 years was tiny. If you just give it time, it will grow and grow and grow and grow and grow all the way to 600 years, after which it starts decaying. The North Pacific is really big, really early, and then just keeps on growing. Interestingly, is that, for instance, the South Atlantic garbage patch just deflates. If you would stop polluting tomorrow, in a few hundred years' time, I don't know why we would really care about that time scale, but in a few hundred years' time it would be gone. There would be no more garbage patch in the South Atlantic. And that is because there's convergence by the large-scale flow, but at the same time there's all this chaotic nature of the flow. The eddies, the vortices are pushing things out again. So it's quite interesting to think about what that means, and we're now working much more on that. So finally then, about like large-scale patterns, is that this method is so easy. This tracing plastic through the ocean is so cheap to do that actually we made it into a website. And I hear you now all thinking, well, what happens to my plastic if it goes from Cornwall? The good thing is you can just do that. You go to adrift.org.au, you click on Cornwall there, and it will compute you live the pathway of plastic from that point. Like here, over 10 years time scale. So you see that all our plastic first kind of hangs around in the Gulf of Biscay, and from then slowly moves into the gyre of the Atlantic Ocean until it hits Florida and Cuba, essentially. So that's the pathway of the plastic moving around. But crucially, to link this then back to what I started with about the pairs of buoys and the quick separation, that separation is why you get this enormous tongue. Why, if you start in Cornwall, 10 years later, you can be roughly anywhere in the North Pacific. We can't be anywhere in the entire ocean because there's still kind of like finite timescales to go from one location to the other. But the chaotic nature of the ocean circulation itself kind of really stretched that out. So, we've got garbage patches, we've got ocean currents moving around, and we thought we were pretty happy, especially when last year there were 2 papers that came out that used a lot of these naturals, not only in the North Pacific but also in the North Atlantic, all over the place. There's still pretty sparse data, but they really tried hard to get to a number of how much plastic is in their ocean. And this was the first of the pair. It was in PNAS, and you can't read it, but they said something like there's 30,000 metric tons of plastic in the open ocean. And then a few months later, there was a paper in PLOS One that said that there was 250,000 tons of plastic in the open ocean. And it was a big story, right? 5 trillion plastic pieces in the ocean, 250 tons of plastic worth, so floating on the surface of the ocean. And then, earlier this year in April, there came a paper in Science that completely independently, using no oceanographic data at all, but just using waste management data, tried to estimate how much plastic is really going into our ocean. And what they found, and again you can read it here, they found that there was maybe only 5 million metric tons of plastic going into the ocean in the year 2010 alone. So that's 2 orders of magnitude higher flux in 1 year than the entire inventory in the open ocean. i.e. 99% of our plastic is missing. i.e. the amount of plastic on the surface of the ocean is tiny, tiny compared to the amount of plastic anywhere else in the ocean. Skip this. This is my own work, but it's actually rather boring. So before I come back to that thought, where's our plastic? I first want to say something about impacts, right? So I've tried, hopefully, kind of started dispelling the myth of the plastic islands by saying, well, there's not that much plastic at all, and certainly it's not the majority of plastic. It's actually a tiny, tiny fraction of all the plastic. But then the other problem maybe it's not about the amount of plastic, maybe it's about the impact of plastic, right? In the end, we don't care about where plastic is, we care about where plastic does harm to marine life. And that's one of the study we published 2 months ago, also in PNAS, where we addressed exactly that question. So we asked, in this case for seabirds, we asked ourselves, where do seabirds forage? And we created a big map of all this. It was a huge literature study. Where are all the seabirds foraging, and how do they do that, and then how much plastic do they ingest? How much plastic does every type of seabird on average have in its stomach? Using over 160 or so peer-reviewed papers to analyze that. And then we compared that map to a map of where the plastic actually is. So we could calculate the risk of plastic to seabird foraging. On a pixel by pixel basis, we could say, well, in this area, there's a really big chance of a species of seabird actually being affected by plastic. In this area, it's not. And that map looks like this. And to me, what stands out is that the garbage patches don't stand out. There's no elevated risk in the areas where we know that all the plastic is. There's an elevated risk, especially here between New Zealand and Australia, but also here in this area around the Kerguelen plateau. Essentially because birds don't forage in areas where there's plastic. And it's not because they want to avoid the plastic, but it's actually because the areas where plastic accumulates are what we call oligotrophic. There's hardly any nutrients there anymore. These areas are kind of like the deserts of the ocean. And some marine biologists, well, almost everybody except for the people that actually study those areas, think of them really as deserts. There's hardly any life, there's hardly any plankton, there's hardly anything to sustain growth because there's no nutrients anymore by the time the plastic comes there. So this might be actually a good point to explain why are there garbage patches. So garbage patches essentially emerge because the ocean circulation itself is not two-dimensional. The ocean circulation is three-dimensional. And there's areas where water comes up to the surface, mainly around the equator, Southern Ocean, around our coastlines. And as it comes up to the surface, it brings on a lot of nutrients from the deep ocean. As it goes, as it does that, it sustains phytoplankton. The phytoplankton start to grow just like if you put nutrients into your, or fertilizer into your garden, that actually makes things grow. And then as the water has moved to the surface, it starts moving around on the surface itself. And it slowly, because of the winds and the rotation of the earth and everything, it slowly starts circulating inward until it gets here in the middle of the gyres. And there it starts sinking. Now, two things. So, as it starts sinking, the plastic is too buoyant. It can't sink with the water itself. So, I am on Radio 4 saying that plastic accumulation is like the turd that won't flush. Which was my highlight. Yeah, we were just talking about what kind of nasty things you can say on Radio 4. This is my personal highlight. Dirty things. So the plastic accumulates because it doesn't sink with the water. But at the same time, because the water is so old, all the nutrients have been used already, so that's why you get these deserts of the ocean in the same place. So seabirds don't really forage there because there's nothing to eat for them. A few weeks later, we did another study on turtles, and exactly the same thing. Turtles get impacted near where they live, near where they forage, not really in the garbage patch. It's slightly less clear in the case of turtles. Skip this. So then, the final nail in the coffin, I guess for everybody who thinks about garbage patches have problems, is to then think about, well, but maybe it's just a good way to clean them up. Maybe if you want to clean them up, why not clean up the garbage patches? And I'm not sure how many of you have heard of the Ocean Cleanup Project and this other crazy Dutch guy, Boyan Slaat is his name, who wants to go out there. It's a huge crowdsourced funding campaign. It was very, very successful, got millions and millions of euros. Did a really good job, by the way, of putting the problem on the agenda and really kind of like made a lot of people aware through Facebook, through Twitter, through Instagram, whatever, about this problem of plastics. So this is now going ahead, and the Ocean Cleanup Project is thinking about going out into the garbage patch, the North Pacific garbage patch, because it's the biggest one, and they are going to put booms into the ocean. Booms like this that sit still on the ocean. So the smart thing about Boyan, which was actually really smart, he was 17 years old, he did it as a high school science project, is that before everybody who was thinking about plastic, about cleaning up plastic in the ocean, was confronted with the problem that if you want to clean up the ocean, you need a big ship and you need to kind of like sail through it and you need to go back and forth. And that just takes a lot of diesel, so you're replacing one problem, namely plastic in the ocean, with the other problem, namely climate change. And who wants to do that? Now what Boyan said is, well, why would you want to go through the ocean if you can have the ocean go through you, right? Why move around with a ship if you can have the currents move through you if you have some booming system? And that's what they came up with. They came up with this idea of booming off essentially 400 kilometers of the North Pacific. And in an artist's impression, it looks like this. So it's a big thing here, and it collects all the plastic, and every few years or so they come back, they scoop all of this out, and they sell it. And there is probably a market for that, because everybody wants to have clothes made of ocean plastic, or it's a bit of a marketing thing, probably more than actual proper economic value, because plastic by the time it's here is really degraded and not really very useful anymore. But it's probably arguably that you can do something like it. Now, but again, to highlight you, this is what the garbage patch looks like, right? So it's really, really thin, and it is not really at the location where you want, because it is at the end. If you think about the impact, so the impact, I hope to convince you, is in the areas where we have a lot of sea life, where we have a lot of marine life, a lot of things going on. Think about the seabirds, the turtles, but also other species. We're doing it for fish now. So if you clean up the garbage patches, you're essentially putting the horse behind the cart. You're fixing a problem after the harm is already done. So this summer, I had a summer student, a second year physics Europe student, Peter Sherman, and who actually in 10 weeks did a whole project, and we actually wrote a paper about this. We're now doing the revisions. It's actually going to be published in environmental research letters, probably. It's fascinating. With the idea of, if you think that yes, you can clean up the ocean, yes, these booms work, where would you want to place them? right? Would you want to place them right in the center of the garbage patches, or would you want to place them somewhere else? So the ocean cleanup project has always talked about the garbage patches. We thought, like, maybe it's better to clean up the plastic with these booms right off the coastlines. So he did this in a model. He tried playing around with where to put these booms, and he came up with this map. It's just one solution of putting 29 booms somewhere in the ocean. Essentially what you have to do is you have to cordon off China. That goes a long way into solving the problem. And then he showed that actually, if you, so here's the amount of plastic in the ocean over time. So we assumed that they would be in the ocean for 10 years. And you start out with a certain amount of plastic here because that's already in the ocean, that's what we know. And if you don't do anything, it would just grow along this black line. Now if you put those 29 things all in the North Pacific, the best solution you can find about the amount of plastic you can reduce is this orange line. But if you put them, say, here, and we don't say that this is actually the best way, it's actually, if you think about it, so we have 29 booms, we have 30,000 ocean grid cells, so there's 30,000 to the power 29 possible solutions of putting these booms. So we can't explore the entire phase space. We can't say that this is the optimal solution, the optimal location of these booms. But we can say that this location is already much better than what the ocean cleanup is proposing. They can clean up roughly 10% or so of the plastic. We can maybe clean up 20% in these locations. More importantly, you can also think about, well, what is the harm, the reduction in harm? What's the reduction in the overlap between plastic and net primary production? So we use net primary production as kind of a proxy of ecosystem strength, ecosystem health. And then for each grid cell, we can look at how much overlap is that. What's the convolation of plastic and NPP? And if you look at time series of that, then again, black is if you do nothing, yellow is if you do it in the North Pacific, blue is if you do it off coastline, if you do it in a more optimal location. And it really seems to be that you get a big, big reduction south of it. So I've got 5, 10 more. Okay, cool. So then before I end, I want to really briefly tell you something about another problem, a much less discussed problem, which I think is some way related to plastic, but in some ways also not, and I think is a much easier to tackle problem. It's going to be really hard to solve the whole plastic problem, but it is relatively easy to solve the problem of ghost nets. So ghost nets are abandoned fishing nets. They are nets that get cut off fishing vessels. So a fishing vessel sails around and then for some reason it has to cut its nets. And sometimes that is for a legitimate reason. Maybe the vessel got into a storm and it got caught in a storm and the only way to save the vessel was to cut off the nets. Very often it's not legitimate reason, and mainly it is about piracy. It is about illegal fishermen fishing around, seeing a naval vessel pop up somewhere on the horizon, quickly cutting their nets. Once the naval vessel is around, they say, oh, we're doing nothing, we're just hanging around, enjoying the sun. So probably 90% or so of these nets are from illegal fishing. The problem is these nets are meant to destruct. They are meant to be very, very tough, very resilient. They are almost impossible to break down. And they are essentially magnets of fish attraction. They are designed to kill fish. Think about it, right? What's also happening probably is it actually, so this is one of them, and it's actually the iconic photo of what the garbage patch looked like. I would say this is a ghost nest rather than a garbage patch. Here's a shark. That shark, I mean, you don't know of course, but it might very well be there because this thing is full of dead fish. Here again, a dead turtle in a net. So they become these attractors of predators because there's all these dead things tangling onto it. They can sit around or float around for decades. And they are a really big problem. And the big source of those is in what's called the Arafura Sea and the Gulf of Carpentaria. So here's the tip of Australia, here's the Australian EEZ, and then here sits New Zealand. And this is all the illegal fishing going on. This is all the illegal fishing. And these are the ghost nets. And the Australian Navy has a real problem getting them. At one point, they actually called me because there was such a big ghost net that they found in the Gulf of Carpentaria. It was more than 100 meters long. And they couldn't do anything with it. They couldn't haul it in because their ship wasn't big enough. In the end, what they did, a colleague of mine suggested that, just to put a drifter on it. So one of the drifters, they attached it to the net. And that net we can now follow. It's just, I think it's beached now, but it has floated around in the Gulf of Carpentaria for 3 years. Just moving around, kind of like catching fish as it goes and as it goes. And there was nothing we could do about it. We know where it is. So I think that this is something really that we should pay more attention to. I think it is easier problem to solve because in the end it is about really illegal activity, right? Litter bugging is just an accident. Microbeads, well, that's been solved largely now, but the fibers from your clothes, there's not really much we can do about it. It's all technology. This is just about getting our act together and stopping this terrible thing from happening. So just to wrap it all up then, what is this problem about? And I'm going to summarize the whole problem by saying what the grant that I'm now actually writing. So I've been stuck in a room for a few weeks now, writing a big ERC grant. And what I want to do is I want to understand the entire pathway of plastics in our ocean. So it's all about how plastic moves around the ocean. And the idea is that if you have an ocean, there's plastics on the upper ocean, but that's only 1% of the amount of plastic that has ever gone into the ocean, remember? Then, so where's the other plastic then? Well, some of it might be in the deep ocean. Some of it might actually be sinking slowly down, either by itself or through biofouling or maybe through fish poop, where it just sinks as it gets incorporated into what we call marine snow, which is essentially fish poop. Some of it might actually be in marine life. Well, I mean, we know that there's plastics in marine life, and we know that that's a problem. And a lot of it might be on coastlines, or at least some of it might be as coastlines. Then we know about the sources. Well, we know that some of the plastic actually comes directly from beaches, comes from people who are on beaches and leave their stuff behind. But most of the sources is actually rivers, shipping, just human activity, rivers putting water directly into the open ocean, and plastic into the open ocean. And then there's all these fluxes between them. The sinking and maybe even resuspension as plastic, kind of like the plankton living on the plastic that make it to sink as they get remineralized or as they get eaten away by bacteria. Essentially, the plastic become buoyant again and they start going back up. So you can get some kind of yo-yo experience maybe about the plastic going up and down. There's, of course, plastic in the ocean itself, moving around on currents, on waves. We don't really know. I mean, we know roughly how it moves on currents, but we certainly don't know how plastic moves around on waves. And for the ones who were here for Adrian's talk, I mean, he studies bubbles. I would love to see the same kind of things in plastics and how they move. Then there's the interaction with the marine life, the ingestion, the excretion, and there's the marine snow, as I said, and finally there's the beaching and the recapturing. So my ultimate goal, I guess, where I want to be in 5 years, is that we actually have a full model of this, that we have a virtual model of tracking plastic through all of these compartments. And we can really try and understand where plastic is, that we know where the 99% of the other plastic is. 1% is here, where's the rest? How are these fluxes? How are they moving? How is all of this going to change the climate maybe even? That's a big question. And all of this is about tracking ocean plastics in our sea. Thank you very much. So I think that, so if you think about here, so in the upper ocean, almost everybody does these trawl nets. And there's a lot of people that do that. Actually, so this guys I skipped over when I said this is my own stuff, that's boring. That was about actually doing this for all the data we could get our hands on. 11,000 of these trawls, and kind of like doing a robust statistical analysis of the numbers you get to, which is essentially still only 1% of the flux. So essentially we didn't really change the numbers, but we did it very thoroughly because we used everybody's trawl data actually. Then in marine life, I mean, sometimes you get people cutting open animals and and looking at the amount of plastic. The problem, of course, is that it doesn't really tell you the flux of plastics through an animal. It can be that if you find a gram of plastics in a fish, you don't know whether that's only been there for a few hours or whether that's been there for a few days or a few months or weeks, right? So very, very little data on that. Deep sea and ocean floor, even less. And there's somebody here at the Natural History Museum, Lucy Woodall, who's actually one of the very first to go down to a sediment core deep in the open ocean and found huge amounts of particular fibers on the ocean floor. But that's just one location, one time go. So we're really in the dark, literally in the open ocean. And on coastlines, you would think that that's the easiest to get data, but the problem is, especially in Europe and especially here in the UK, coastlines get cleaned up way too often. And if they get cleaned up, well, maybe not way too often, but way too little scientifically. Councils don't weigh the amount of plastic that they take out of coastlines. I would love to convince a council like Brighton to actually properly, it's fine if they take away the plastic, but at least weigh it, at least characterize it, at least give us some data to find out what the fluxes are in the inventories. So there's a little bit of that, and we're working still in Australia where they did a really cool assessment, literally going every 100 kilometers around Australia. So there's like 60 sites or so, which some of them are remarkably remote. It's really cool to get there. Well, it's really hard to get there. And every time doing the same an assessment of how much plastic is there, doing transects and everything, but that's far and in between. Yeah. They are very much a theoretical thing. So all of this is backed by TU Delft. And there's actually really good engineers working on this. Now, I am not an engineer at all. For the last time I did any lab work was in second year undergrad physics. So I don't know. I can't comment about how realistic I mean, I would be slightly skeptical about the scale of the problem, right? If you want 500 kilometers of boom, the amount of deep sea anchors that you need for that is, I think I once did the calculation, back of the envelope calculation, that's 10 times more deep sea anchors that are used in all of oceanography now. So you suddenly need a huge amount of stuff just to have 500 kilometers of boom going around. But our study wasn't really about that, right? Our study wasn't about the engineering. It was about just the whole concept. I think really it's about putting the horse behind the cart. Again, very, very little. Actually, no, not that little. There was a paper that came out 2 years ago by an Australian again, who didn't use one trawl, but actually used 10 stacked on top of each other. And then looked at how each trawl got different data. And then compared that to wind depth. And there are some models now about how plastic changes with wind depth. We don't really know how that depends on type of plastic, for instance, or how that depends on shape of plastic. But there's actually in all of this, that's probably my least worry, because there's actually really good understanding and theoretical model about drag forces on stuff, especially oil droplets, those kind of things. Yeah.
So when you compare the maps of the seabird corridors and the amount of plastic you find, you said it was not like climate. Is that not what you expect to find if the seabird is not full of plastic? And they're taking it away, so you don't find it.
That's an interesting comment. Yeah, well, so the assumption we work with, and that I always had in my head, is that seabirds will never clean up the entire ocean, right? So again, if you think about the amount of plastic in the ocean, and most of it being very so garbage patches, like a really, really, really dilute soup of tiny, tiny microplastic floating around, I wouldn't really see how seabirds could efficiently take all of that out. Yeah. Well, yeah. My intuition would be that if you just count how much water seabirds gulp up all the seabirds in the world versus how much water is in the upper 5 meters of the ocean, I think that would be a very, 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 very small percentage. But that's, yeah, I mean, it's a good point. Yeah, it's interesting. Yeah.
Thanks for your talk. You mentioned at the beginning 3 different kinds of plastics, like the larger ones and micropieces. Do they behave differently? Do they move around differently? Do you more microfibers at the coast or something like that?
We don't know. We don't know. I expect yes. I mean, so especially talking again about kind of like mixing and what wave and breaking waves do. Larger stuff has more buoyancy, stays higher up. If it's really large, it can actually have windage, and it can actually be moved by the wind itself rather than by the ocean currents. So yes, different sizes behave differently, and we will have to take that into account in our modeling. I think the other thing is that different sizes have a different ecotoxicological effect. Nanoplastics might do something really different in an animal than microplastics or even bigger kind of like lighters in a bird. So one of the things, actually, so of that bird work, that was mostly really big stuff because we started out in the 1960s. So the first publications we found were in the 1960s were not targeted for plastic. Those were studies where people, ornithologists, cut up a bird to see what it had eaten. And every now and then they found a piece of plastic, and then they would report it in their paper as kind of an oddity. But it was all very, very visual and we tried to keep that through the entire study, not to kind of like get a bias where people actually start digging around and finding smaller and smaller stuff. We did in the press release of that paper, we talked about if you have the average amount of plastics that's in the gut of a seabird, if you would scale that up to that seabird to be as large as a human being, that would be 6 kilos. So it's a bit like walking around with two fat house cats everywhere you go. And then we walk around; they actually fly around. So I think we made a case that we think it has a really big impact on the energy consumption. And it's probably more important especially for seabirds, than the ecotoxicological effects.
I'm intrigued about the fact, you mentioned, of course, when you kind of focus things in the center of the gyres, those are natural places where we have downwelling. So if you think that the plastics, by the time they arrive there, are of course quite degraded, and they're probably more like in nanoform or something.
Yeah.
And taking on that people have found plastic actually in deep sea creatures as well.
Yeah.
Isn't there the bigger problem lurking? It's not just, what's taken out of the surface, but what gets into the deep sea chain and the food chain actually of the deep ocean, and then transports all around the globe in a very different way than your surface current?
True. But I don't think anybody has any reasonable guess about whether there's more plastic in this reservoir or in this reservoir. I think this is the biggest question mark of me. My hedge would be on this one, actually, that 95% of the plastic is in this. And as I said, we're now doing a study where we use that entire Australian data set of how much plastic is around the coastline every 100 kilometers and relate that to population density. And there's a remarkably good correlation if you assume that plastic just gets washed up within the first 10 days. Then you get you explain a really large amount of spatial variability. So that doesn't prove anything, but it does say that under the assumption that plastic just washes back immediately, at least in Australia, we get a pretty good correlation between where we think it enters the ocean and where it ends up. So I would say that 95% maybe, 90% is here.
Have you mentioned black spoons or midnight?
Yeah.
Has been much work done sort of saying how much microplastics go through bigger animals? I've seen packaging studies, I guess there's less ethical things to do. But is there much understanding of how much
No. We don't really know even. No. That's the answer.
Well, that's an interesting answer. No, I know that. Thank you very much. I know that a few other people have questions, and so there's no reason to stop you asking them. But after we've concluded doing here, and after we're having a drink, I think that's the appropriate time. So join me in thanking Erik once more for really.